Hello students, welcome to EPG Pathshala. I am Dr. Anjali Sharma from University of Delhi. Today we are going to discuss about the module Radiation by Point Sources Part 1 from paper Electromagnetic Theory. From this module you may get to know about the following: the calculation of radiation by moving sources from electromagnetic fields obtained in the previous module, radiation and its angular distribution in the non-relativistic case, that is Larmor formula for emitted radiation. Total radiation in the relativistic case obtained from the generalization of the Larmor's formula. Radiation losses in charged particle accelerates, linear and circular accelerators. Angular distribution of radiation in the relativistic case, study of two special cases, acceleration parallel to or perpendicular to velocity and their comparisons. As we have emphasized again and again, one of our main tasks is given a source to find the fields and ultimately the radiations produced by it. The sources can be localized charges and currents like waveguides, the input from which is fed to the antennas to produce radiation. Alternatively, we have a charged particle or more like a beam of charged particles moving along a given trajectory and possibly emitting radiation during its motion. This is the case that we are considering now. Here, gamma is the Lorentz boost vector, that is 1 divided by under root of 1 minus v square by c square, and r is equals to x minus r equals to r into n cap, and ref after the square bracket implies that the entire expression is to be evaluated at the retarded time tau naught given by x minus r tau naught whole square is equals to 0, and the retardation requirement x naught greater than r naught dependent on tau naught, and tau being the proper time of the particle. An accelerated charged particle produces radiation. Radiation is the irreversible flow of electromagnetic energy from the source to infinity. This is possible only because electromagnetic fields associated with accelerating particles falls off as 1 upon r rather than as 1 upon r square as in the case of charged rest or moving uniformly. So the total flux obtained from the Poynting vector is finite at infinity. The instantaneous energy flux is given by the Poynting vector S is equals to E cross B divided by mu naught, which is equals to 1 divided by mu naught C into E cross n cap cross E is equals to 1 divided by mu naught C mod of EA square n cap. This is the power radiated per unit area along the radius vector. The radially outward power output per unit solid angle is dP divided by d omega, which is equals to r square into S vector dot n cap equals to 1 divided by mu naught C mod of r into EA vector square equals to E square divided by 4 pi epsilon naught into 4 pi C whole into mod of n cross beta dot whole square. On substituting for EA, if theta is the angle between the acceleration v dot equals to c beta dot and n cap, then the power radiated can be written as dP by d omega equals to E square divided by 4 pi epsilon naught into 4 pi c cube whole into v dot square sine square theta, where sine square theta depends on the characteristic of dipole radiation. It is just dipole results in disguise, polarization in the plane containing v dot and n cap. The total instantaneous power radiated will be P equals to integral of dP by d omega into d omega equals to E square divided by 4 pi epsilon naught into 4 pi c. Larmor's formula. Let us now find the radiation produced by such a charged particle. The first term in E xt, the velocity field falls off as 1 divided by r2 and does not produce radiation. It is the second term which is responsible for radiation. Let us first calculate the radiation produced by a particle which is accelerating but is observed from a frame of reference in which its velocity is small, that is b is very less than 1. Not dp by d tau is equals to gamma dp by dt equals to gamma d of mc gamma beta by dt equals to mc bracket gamma raised to power 4 into beta dot beta into beta plus gamma square into beta dot bracket close. Beta dp by d tau is equals to mc gamma raised to power 4 beta dot, and this implies that p is equals to 1 divided by 4 pi epsilon naught 2 by 3 e square by c gamma raised to power 6 bracket beta dot square minus beta cross beta dot whole square bracket close. This is also called Larmor formula for power radiated by a non-relativistic accelerated point charge. The power radiated is independent of the sign of charge as well as whether the particle is accelerating or deaccelerating. Obviously, a charged particle moving in a circular orbit, even with a constant speed, is accelerating all the time and hence must radiate. Classically, this applies to an atom as well, in which case the electron moving in an orbit around the nucleus should continue to radiate, lose energy and eventually fall into the nucleus. Of course, nothing of the kind happens. The fact that we exist is proof of that. This was one of the major paradoxes of classical physics, which was ultimately resolved by the advent of quantum mechanics. But that is altogether another story. Now let us see about the relativistic generalization of Larmor's formula. Larmor formula for total power radiated can be generalized to arbitrary velocities by arguments above covariance under Lorentz transformation. Radiated electromagnetic energy, like mechanical energy, is the zeroth component of a 4 vector. Similarly, time is the zeroth component of position 4 vector, and it seems plausible therefore, and it can be shown more rigorously that their ratio, the power radiated P is equals to dW by dt, is a Lorentz invariant quantity. If we can find a unique Lorentz invariant which reduces to Larmor formula in the limit, then we have our desired generalization of the formula. There are many Lorentz invariants that reduces to Larmor's formula in the non-relativistic limit, but there are some other constraints that have not to be met. Linear accelerators. Let us look at linear accelerators first. In this case, motion is one-dimensional and acceleration is along the direction of velocity. So, beta cross beta dot is equals to 0. So, this implies that P is equals to 1 divided by 4 pi epsilon naught into 2 by 3 E square by m square c cube bracket dp by d tau whole square minus beta square into dp by d tau whole square bracket close, and this is further equals to 2 by 3 e square by m square c cube 1 minus beta square into dp by d tau square, which is further equals to 1 divided by 4 pi epsilon naught 2 by 3 e square by m square c cube dp by dt square and it is again equals to 1 divided by 4 pi epsilon naught 2 by 3 e square by m square c cube dE by dx whole square. So power radiated depends on rate of energy supply, not on energy, and power radiated is inversely proportional to the square of the mass of the particle. One area of application of relativistic expressions for radiated power is that of charged particle accelerator. In accelerators, energy is provided to accelerate the particle to high energies to perform scattering and other experiments with the beam of particles. In this context, any energy radiated away is an unavoidable loss, and sometimes it is the limiting factor on the maximum energy that a beam can achieve. For a given force, that is, a rate of change of momentum, the radiative power depends inversely on the square of the mass of the particle, and consequently the radiation losses are the maximum for the electrons. The ratio of power radiated to power supplied by the source is given as P divided by dE by dt equals to P divided by V into dE by dx equals to 1 divided by 4 pi epsilon naught into 2 by 3 into E square by m square c cube into 1 by V into dE by dx, which tends to 1 divided by 4 pi epsilon naught 2 by 3 into E square by mc square divided by mc square into dE by dx, where the last form holds for relativistic energy, so that V tends to C. The loss of energy due to radiation is maximum for the electrons. Let us use units that are appropriate for high energy physics. So mc square equals to 0.511 MeV is the rest energy of the electron. The quantity E square by 4 pi epsilon naught mc square has the dimensions of the length and is the classical radius of the electron. It has the value 2.82 into 10 raised to power minus 15 meters. The typical energy gains dE by dx are of the order of 10 MeV per meter. Thus, P divided by dE by dt is approximated to 10 raised to power minus 15. Radiation losses in linear accelerator are completely negligible even for electrons, not to talk of heavier particles like protons and nuclei. The energy loss due to radiation is no issue for linear accelerators. Circular accelerators, that is synchrotron radiation. Circumstances changes dramatically in the case of circular accelerators such as a betatron or a synchrotron. In such accelerator, a magnetic field keeps the particle moving in a circular path at two diagonally opposite points. Along the circular path, the particle is accelerated through an applied potential differences. Synchrotron radiation is the name given to the radiation which occurs when charged particles are accelerated in a curved path or orbit. Classically, any charged particle which moves in a curved path or is accelerated in a straight line path will emit electromagnetic radiations. Various names are given to this radiation in different contexts. For example, when it occurs upon electron impact with a solid metal target in an X-ray tube, it is called Bremsstrahlung. In the application to circular particle accelerators like synchrotrons, where charged particles are accelerated to high speed, the radiation is referred to a synchrotron radiation. This radiation energy is proportional to the fourth power of the particle speed and is inversely proportional to the square of the radius of the path. It becomes the limiting factor on the final energy of particles accelerated in electron synchrotrons like the LEP at CERN. However, in other contexts like The detected arrays in accelerators, it can be detected and used as an aid to analyze the products of the scattering event in the accelerator. Typically, in such machines, the energy gain per rotation is small, but the momentum changes rapidly along the circular path. This means that mod of dp by d tau is equals to gamma omega mod of p, much greater than 1 by c dE by d tau. Here, omega is the frequency of gyration of the particle in its circular path. As a result, the second term is negligible, so that minus of dp mu by d tau dot dp mu by d tau is equals to dp by d tau whole square minus 1 by c square into dE by d tau whole square can be approximated to dp by d tau whole square. So this implies that power radiated P is equals to 1 divided by 4 pi epsilon. The radiative energy loss per revolution, that is delta E is equals to 2 pi by omega P equals to 2 pi rho by C beta into P is equals to 1 divided by 4 pi epsilon naught into 4 pi by 3 E square by rho into beta cube gamma 4. Now E is equals to gamma mc square, and for high energy electrons beta can be approximated to 1. So delta E is equals to 1 divided by 4 pi epsilon naught 4 pi by 3 into E square by rho into E by mc square raised to power 4. Thus, delta E in MeV is equals to 8.85 into 10 raised to power minus 2 into E raised to power 4 with units GeV divided by rho meters. In the first electron synchrotron built in 1950s, the radius was first around 1 meter and E maximum was around 0.3 GeV. Hence, delta E maximum was around 1 keV per revolution. This was less than but not negligible compared to the energy gain of a few keV per turn. In the 10 GeV kernel electron synchrotron, the orbit radius rho was around 100 meters and the radio frequency voltage per turn was 10.5 MeV at 10 GeV. According to the above estimate, the energy loss per turn is 8.85 MeV. Thus, at this energy, almost the entire power supplied is radiated away. So, this put a limit on the maximum energy that could be achieved. In 1990s, LEP had E maximum approximately equals to 100 GeV, rho effective equals to 2300 meters, which implies that del E max equals to 3.3 GeV, which is an enormous energy drain, much more than supplied to a city like Delhi. Synchrotron radiation have numerous use in the study of atomic structure, chemistry, condensed matter physics, biology and technology. Angular distribution of radiation. As we have seen earlier, for non-relativistic motion, the radiation emitted by an accelerated charge has a simple sine square theta dependence. For relativistic motion, the acceleration fields depend on velocity in addition to acceleration. So, angular distribution here is more complicated than for non-relativistic case. So, the radial component of Poynting vector can be calculated as S dot n cap equals to 1 divided by mu naught C into mod of EA square equals to E square epsilon naught divided by 4 pi big bracket 1 by R square mod of n cap cross bracket n cap minus beta cross beta dot bracket close divided by 1 minus beta dot n cap whole cube, and the mod is square and bracket close. The radiation by the charge from time t dash equals to t1 to t dash equals to t2 reaches a surface surrounding the charge from time t equals to T1 plus RT1 by C to t equals to T2 plus RT2 by C. The power crossing a unit area at x on the surface S at time t is S xt dot n cap, where n cap being the unit outward drawn normal. So the total energy crossing this unit area during radiation by the charge is W equals to integral from t equals to T1 plus RT1 by C up to t equals to T2 plus RT2 by C of S dot n cap dt equals to integral from T1 to T2 S dot n cap dt by dt dash into dt dash. So we identify the integrand of this expression S dot n cap dt by dt dash as dw by dt dash, that is the rate at which the charge radiates what eventually passes a unit area on S at the point x. This is the instantaneous power radiated, hence dp t dash by d omega equals to r square S dot n cap dt by dt dash equals to r square S dot n cap into 1 minus beta dot n cap. If the charge is accelerated for a short time, during which beta and beta dot are essentially constant in direction and magnitude, now far away from the particle, n cap and beta are also constant during the period of acceleration. Then the angular distribution of radiation is given by dp t dash by d omega equals to 1 divided by 4 pi epsilon naught into E square by 4 pi C into mod of n cap into bracket n cap minus beta cross beta dash bracket close whole square divided by 1 minus n cap dot beta raised to power 5. Integration over the solid angle in this general case is rather involved. However, it can be performed, and the relativistic generalization of the Larmor's formula could be resulted out. Acceleration parallel to the velocity. There are two special cases. First is the acceleration parallel to the velocity, where beta cross beta dot is equals to 0, which leads that dp t dash divided by d omega is equals to 1 divided by 4 pi epsilon naught into E square v dot square divided by 4 pi c cube into sine square theta divided by 1 minus beta cos theta raised to power 5. The total power radiated can be obtained by integrating the above equation over d omega, and elementary integration yields P is equals to 1 divided by 4 pi epsilon naught into 2 by 3 E square V dot square divided by C cube gamma raised to power 6. In the non-relativistic limit, that is beta much less than 1, this reduces to the Larmor's result, but as beta increases, the angular distribution is tipped forward more and more, and at the maximum, the power increases in magnitude. The angle at which the intensity is maximum can be obtained by differentiating the above equation and equating to 0. So on putting cos theta equals to u and differentiating with respect to u, we have theta max equals to cos inverse of 1 divided by 3 beta into under root of 1 plus 15 beta square minus 1. So for beta tending to 1, theta maximum could also be tends to 1 divided by 2 gamma. Thus, there is a sharp peak very close to the forward direction, though exactly in the forward direction the power emitted is 0. However, theta max can also be so small that for all practical purposes the peak is in the forward direction. So for small angles theta close to theta max, angular distribution is simplified to dp t dash by d omega equals to 1 divided by 4 pi epsilon naught into 8 E square V dot square divided by pi c cube into gamma raised to power 8 into gamma theta whole square divided by 1 plus gamma square theta square whole raised to power 5. So peak occurs at the point gamma theta equals to half, and half power points at gamma theta equals to 0.23 and gamma theta equals to 0.91. So finally, the root mean square angle of emission can be obtained by integrating the above equations, and we get time average of theta square raised to power half equals to 1 divided by gamma equals to mc square by E. Second case is the acceleration perpendicular to the velocity. So a particle in instantaneous circular motion has its acceleration perpendicular to its velocity. Let us choose the instantaneous velocity to be in the z direction and acceleration in the x direction. So that beta equals to beta e cap 3 and beta dot equals to beta e cap 1 and n cap is equals to sin theta cos phi e1 cap plus sin theta sin phi e2 cap plus cos theta e3 cap. The various vectors and scalar products can now be worked out, and we have n cap cross bracket n cap minus beta cross beta dot bracket close equals to n cap dot beta into n cap minus beta minus 1 minus n cap dot beta into beta dot, which implies that mod of n cap cross bracket n cap minus beta cross beta dot bracket close whole square equals to mod of n cap dot beta dot into n cap minus beta minus 1 minus n cap dot beta into beta dot whole square, and this could be equals to beta square into 1 minus beta cos theta whole square beta square minus 1 minus beta square sin square theta cos square phi. So the power radiated can be written as dp t dash divided by d omega equals to 1 divided by 4 pi epsilon naught into e square divided by 4 pi c cube into mod of v dot square divided by 1 minus beta cos theta whole square whole into bracket 1 minus sin square theta cos square phi divided by gamma square into 1 minus beta cos theta square bracket close. Thus, we observe that the total power radiated can be obtained by integrating the above equation over d omega, and P is equals to 1 divided by 4 pi epsilon naught 2 by 3 e square v dot square divided by c cube gamma raised to power 4. So, in this case, there is radiation in the forward direction, that is theta equals to 0. The detailed angular distribution is rather complicated as two angles are involved. However, the same characteristic relativistic peaking in the forward direction is seen. Taking the ultra relativistic limit gamma much greater than 1, as we did in the case of linear motion case above, we get dp t dash by d omega equals to 1 divided by 4 pi epsilon naught into 2 e square by pi c cube into gamma raised to power 6 into v dot square divided by 1 plus gamma square theta square whole raised to power cube into bracket 1 minus 4 gamma theta square cos square phi divided by 1 plus gamma square theta square whole square bracket close. The root mean square angle of emission can be obtained exactly in the same way as done before, and is average of theta square raised to power half equals to 1 by gamma equals to mc square by E, and it is exactly the same as in the earlier case. Comparison of two cases. Now, from the expressions for the total radiation produced in the two cases, we observe that for a given acceleration, the radiation produced in the parallel case is a factor gamma square more than in the perpendicular case. However, the statement is somewhat misleading because what is supplied is the force and not the acceleration. So a given force produces quite different acceleration depending on whether it is applied along or transverse to the velocity. So for a force parallel to the velocity, F is equals to dp by dt equals to m gamma cube dv by dt. On the other hand, for a force applied normal to velocity, F is equals to dp by dt equals to m gamma dv by dt. Hence, expressed in terms of dp by dt, the power in the two cases are P perpendicular equals to 1 divided by 4 pi epsilon naught into 2 by 3 E square by m square c cube gamma square into dp by dt whole square, and P parallel equals to 1 divided by 4 pi epsilon naught into 2 by 3 into E square by m square c cube into dp by dt whole square. Thus, for a given force, the radiation produced is a factor gamma square more than the forces applied perpendicular to the velocity than what is applied parallel to it. Of course, if the force comes from a magnetic field, it is always perpendicular to the velocity. So students, let us summarize what we have learnt in this module. The derivation of radiation by moving source from the electromagnetic fields obtained in the previous module is given. The non-relativistic limit of the expression for radiation is obtained, leading to Larmor's formula for total emitted radiation. The total radiation in the relativistic case is obtained from the unique generalization of the Larmor's formula. The radiation appears as losses in charged particle accelerators. Such radiation losses are discussed for linear and circular accelerators. Angular distribution of radiation in the relativistic case has been derived, and the two special cases, that is acceleration parallel to and acceleration perpendicular to velocity, are discussed, and a comparison of the losses in the two cases has been made. Thank you.